Hello everyone, welcome to today's video, which is an introduction to exponential functions. If you would like at this point to pause this video, try the 4 warm-up problems to make sure that you fully understand the properties of exponents before we get into graphing them. Pause the video now, come back and check when you're ready. Okay, and here are the answers to the 4 warm-up problems. Hopefully you got those right. If not, I do encourage you to go look up how to solve Algebra 1 problems using the properties of exponents. But for now, let's move on to graphing exponential functions. There are 2 basic types of exponential functions, but they are both in the same form. This right here is the form of exponential functions. And yes, we will transform these functions later on as well. But for right now, that's the basic form of it. Okay, growth happens when that b number is greater than 1. Decay happens when that b number has an absolute value that's less than 1. Okay, growth is exactly what you would think it would look like. It is growing, it is getting larger as x goes to infinity. Whereas decay is the opposite of that. As x goes to infinity, the y is getting lower and lower, usually closer to 0 unless there is a vertical shift. So let's take a look at a couple of these. Here's our first example. A certain cancerous tumor doubles in size every 6 months. If the initial size of the tumor is 28 cells and it goes untreated, how many cells will there be in 4 years? All right, so it doubles every 6 months. Okay, we can use our calculator to help us with this table. Every 6 months or every half year, it doubles. So first we have 28, and then it doubles to 56. And then it doubles to 112. And yes, I am using my calculator to help me with these numbers. 224, 448, 896, 1792, 3584, and then finally, after 4 years, it'll be up to 7,168. So let's plot these points on here the best we can. All right, so 1 comma 112 would be right around there. 0 comma 28 would be even closer to the x-axis. 2 comma 448 would be somewhere around there. 3 comma 1792, probably right around there. And 4, 7,168 would be right above there. If we connect the dots, clearly this is an example of exponential growth. You can see from this function right here, that's exponential growth. Okay? So the explicit formula for this example is going to be exactly like this says right here. We can call it whatever we want. We can call it y, we can call it a, we can call it anything that we want. Let's just go with y here equals a b to the x, where x is your independent variable and y is your dependent variable. Okay. We could also use t for time instead of x. And we could use maybe c for cancer cells instead of y. It doesn't really matter. But what we do know here is that our b is going to be a positive number greater than 1, okay, because it's exponential growth. The domain of this function, well, time isn't really negative, so we're going to start at 0, and it's going to go to infinity. The range of this function, well, it also started at 0, but it's greater than 0, but really we started at 28. So we're going to go 28 to infinity. All right, the next one here, the half-life of caffeine in your body is about 6 hours. If you drink a cup of coffee with 140 milligrams of caffeine at 6 a.m., how much will you have remaining at 6 a.m. the next day? All right, so half-life means that half of it will be gone in 6 hours. So every 6 hours, half of the milligrams will be gone. So if we start with 140, after 6 hours, we'll be down to 70. Another 6 hours down to 35. Another 6 hours will be down to 17.5. And another 6 hours will be down to 8.75. So after a day, you'll still have 8.75 milligrams of that caffeine, that cup of coffee, in your system. If you plot these points, 0, 140, 6, 70, 12, 35, 18, 17.5 would be probably right around there. And then 24, 8.75 would be right around there. And connect the dots here. Should look like this. Okay, this is called exponential decay. As we can see that the graph is going down to 0. The explicit formula is the same formula. The only difference here is that b would be less than 1. Okay, the absolute value of b would be less than 1. All right, our domain, well, it also starts at 0 and goes to infinity. The range of this graph, well, it's going to get closer and closer to 0 without ever actually reaching 0. And it started at 140. So it's going to be parentheses 0, 140 with a bracket. I put an arrow on this part here, but I really shouldn't have because we can't go backwards of time. So really the graph's going to look like this. All right, let's go all the way back to a long time ago when we started talking about transformations of graphs. All right, each of these are one transformation of the graph. Let's hope we remember these. Might be a good idea right now for you to pause this video and try to write down exactly which transformation is taking place. For example, in A, we should have wrote down that this is a vertical shift up 1. All right, so if you want to pause this video now and try the other 9, that'd be a good idea. And come back when you're ready. All right, let's go through these. B would be a vertical shift as well, but this would be down 2. All right, C and D are both horizontal shifts. But remember, for horizontal shifts, it goes the opposite way that you might think. So the plus 3 is actually going to move it left 3. And the minus 4 is actually going to move it right 4. Okay, E and F are vertical stretches and compressions. So for E, that would be a vertical stretch. And we would just say vertical stretch by 5. And then for D, that would be a vertical compression by 1/6. G and H are horizontal stretches and compressions, but remember it's the opposite way that you would think here for horizontals. Horizontals are always the opposites, right? So for G, this would actually be a horizontal compression by 7. And then for H, this one would be a horizontal stretch by 1/8. The last two are reflections. Outside on I, so that's going to be vertical. And the negative is inside the function there on J, so that one is going to be a horizontal reflection. All right, we will need this to graph our exponential functions here on the next slide. We've got 3 examples. First one, there's nothing going on with that one. That's just our base parent function. So let's pick some points here. If we put 0 in, anything to the 0 is 1, so 0, 1. If we Put 1 in, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. What about 2 to the negative 1? 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4. And now you should see this shape taking place here. It should look something like this, with a horizontal asymptote at y equals 0. So the y-intercept here, if you put 0 in, you get 1 back, so 0, 1. Our domain is all real numbers. It'll always be all real numbers for exponential functions, unless it's a word problem, like our first two examples today. The range here would be 0 to infinity, and the horizontal asymptote is y equals 0. Now we're going to transform these functions. B has two transformations taking place. So let's write our rule out where x, y here we go to x plus 3, y plus 2. So what we're going to do is we're going to take those points that we got in part A and move them right 3 and up 2. And the asymptote here will also move up 2. So our graph's going to look something like this. So our y-intercept here, if we put 0 in for x, you get 2 to the negative third, which is 1/8 plus 2. So it's 2 1/8, which we can write as 8 times 2 plus 1 is 17, so 17/8. Our domain, again, is all real numbers. Our range this time is 2 to infinity because our asymptote is y equals 2. All right, and then part C, we're going to be going to the opposite of x and then moving y down 4, which means our horizontal asymptote will also move down 4. All right, so our original point here of 0, 1, 0 stays at 0, and then we move down 4, so 0, negative 3. The other point, our next point was 1, 2, so that'd be negative 1, negative 2. And another point we had was 2, 8. Sorry, 2, 4. 2, 4. So I'll go to negative 2, 0. And you should be able to see now what this graph is about to look like here. Should look something like that. The y-intercept, if we put 0 in for x, we get 1 minus 4, which is negative 3. Our domain, again, is all real numbers. Our range this time is negative 4 to infinity. And our asymptote is y equals negative 4. Okay, so big hint down there that this k will always be your horizontal asymptote. Okay, at this point, there are a couple problems on the next slide I'd like you to try. So pause this video here, try all the problems on the last slide, and then come back together on this video. Hit play to check your answers. And here are the answers to that last slide. Thank you, as always, for watching my videos. I hope you learned something today. Come back another time. Have a good day.